Thank you very much for the nice introduction. My name is Tiger Tao, and as introduced, I'm from Chinese Academy of Sciences, and my major is double E. It's actually in microelectronics in sensors. So today's topic is in the cutting edge research area is brain-computer interface. So I also have a company, a small startup company, focused on commercializing this technology. So today I can show you some background of brain-computer interface, some recent progress. I mean, both worldwide and within our own group, and show you some potential application in terms of clinical applications and for research purpose. Okay. So as we know, at least I believe our brain is the most important organ in our body. However, it's very complex and it's very vulnerable, which means during our lifetime, it's inevitable we're going to suffer from some kind of brain diseases. Okay, so including, for example, we have some disabled disabilities in terms of motion and the language. So, but it's pretty difficult to understand. I mean, fully understand how our brain is working because we have so many neurons within our brain, and all these neurons connected within each other. They have tried to communicate with a lot of information, okay, and some kind of information exchange and so on. So it's a huge, it's a extraordinary network in terms for our for computing, for learning, and for some kind of judgment. Okay, so however, because it's very vulnerable in terms of their uh, some neurons were gonna die due to different reasons, and for between some is internal or some is external. So brain-computer interface as a technology which can get into our brain to understand how our brains function in terms of how the neurons in terms of the electrically and biochemically to understand how they are working and also try to go back to modulate our brain to function properly. So that's how brain-computer interface can offer at this stage. In the future, probably brain-computer interface can do something more, and that's what I'm gonna try to introduce. In my next slide. Back in 2021, the Science magazine proposed a new 125 major scientific questions. Okay, we did a little bit of research in terms of this 125 scientific problems and also scientific challenge. Okay, we found out there are at least 12 challenges are directly related to our to brain science or neuroscience. Okay, part of them is basically on the fundamental research, and the part of them in terms of neural engineering, in terms of how we can, build better tool to understand and also cure our brain diseases. So if we go back, I'm not sure if you can understand the Chinese wording here. So if we go back 1 century, there's some very major, we said, scientific project uh, worldwide back in 1940s. This Manhattan project, that's making nuclear weapons, and Apollo project is making the moon project, and now back in 1980s, there's some kind of human gene project, and now in the new century, I think starting from 2010, and it's called human project, human brain project. So if we take a look into this, huge worldwide science project, you can find that basically they all rely on the development of new tools. For example, for the Manhattan project, we need to get very high level centrifuge machines to do that. Okay, and for the Apollo project, we need to get this rocket, right? And for this, we said the human brain project, we think the brain computer interface may be the key tool to pro, promote this project and try to understand better of our brand. That's why we're working on this. Okay, I'm gonna skip this slide because it's more related to how we, in terms of China, have tried to plan how we're gonna do this brand project in different area in China. Of course, if you know this, Beijing, Shanghai are the two key cities which have invested a lot into this brain-computer interface area. So let's take a look at of brain-computer interface itself. We know, brain-computer interface indeed is an interdisciplinary area. So it's very rely on the merge of biotechnology and information technology. For example, it's basically in two different ways. If we take a look of this so-called BTIT, the biotechnology and info tech. Um, in one way, because as I mentioned, as a human, we we're gonna suffer from this brain diseases, and brain-computer interface has the potential to go into our brain to understand why we have this kind of disease and try to offer a solution to cure this disease by trying to collect the electric signal of our brain in terms of from the neurons and try to modulate basically by stimulating the neurons and try to make them back to normal status. So that's how we can rely on brain-computer interface to treat these brain diseases. Okay, that's one thing we can use brain-computer interface. And also, I think that's basically most of our peer researchers are working now is try to use brain-computer interface to cure brain disease. But if we take a look into the further future, and there's many things we can expect or we can imagine using this technology. For example, as we know, our brain may be the most advanced organ in our body, but other than that, I don't think we as a human being we have the best you know for example, abilities compared to other creatures. For example, we don't have the most powerful part, and we don't have the best speed, and we don't have the best strength, right? Because a lot of other creatures, for example, a lot of animals have better eyesight, have better strength, can run faster than us. So the idea is if we can use brain-computer interface to connect our brain, the most advanced organ in our human being, and try to connect to other uh, silicon-based technology, for example, sensors, actuators, then we can kind of bypass our own body. Just try to use the best part of our body, which is the brain, and to connect our brain to the other advanced technology, sensors, actuators, computers, cell phones. Then we can try to take full advantage of our brand. That's the future in my imagination. How we can try to push brain computer interface to another level. Okay, so however, in the past probably 2 decades, United States, including other countries, they have developed many quite useful brain-computer interface or neural interface to do that, including invasive ones and non-invasive ones. So the way you can uh, differential from invasive one and non-invasive one is basically if you want to insert this neuron probe into the brain. Okay, if you need to, or if you have to go through a neural surgeon to put this probes into the brain. Okay, of course, we can understand if you go further into the brain, you're gonna get a better signal and you're gonna get better accuracy in terms of you want to modulate the brain activities. Okay, but if you go further into the brain, it's gonna have more kind of damage into the brain. So you have to make some kind of trade-off or compromise if you want to apply this technology to different situations. But in terms of those very how to say that? Probably I have to say that in Chinese. 一些绝症，比如说渐冻症, some kind of this kind of disease, you have to go through with the invasive technology, okay, because to get better results. Okay, so as you all know, Elon Musk has get into this area in terms of brain-computer interface. They start up a company called Neuralink. They try to develop this kind of invasive neural probes in terms of array forms. They're gonna put hundreds, if not thousands, neural probes into the brain, try to collect as many signals as possible, and try to rebuild or restore a functionality of a brand. So that's what they have done. Uh, Up to earlier this year, they have completed the first clinical application of their product, and they get pretty good results. And as I heard, they have done the second, probably going to start the third patient with different brain diseases, try to uh, further extend the functionality of their product. Uh, the results are quite expressive because the thing here is, you know, we have so many neurons. We have so many neurons in different part of our brain. So if you can connect more signals, so you can better decode the brain signals and try to uh, carry out the signal and turn it into some kind of activities in terms of motion and the language. In this case, they do it into a motion restoration. And later on, as I heard, they're gonna do vision case. Okay, they're gonna try to apply this to some kind of blind people and try to restore their vision. In terms of China, I mean, there are also some progress from the Tsinghua University have tried to implement kind of wireless brain computer or this kind of neural probe into some patient. But in this case, they only have four channels or four electrodes try to collect this signal and try to perform some kind of motion in this case. Okay, and but there's a lot of things we need to do. I'm gonna skip this political ones, and I'm gonna try to say why brain-computer interface is very challenging. Okay, in two different ways. One, brain-computer interface is indeed interdisciplinary area. It's gonna involve expertise from microelectronics, right? Neuroscience, materials, robotics, and the clinic, medical, something like that. Okay, so if you want to do this, you might need to build up a group with expertise from all this kind of area, and they have to talk to each other, understand each other, and try to work together. That's how we're gonna do this in our group. I have students from all different areas, and I even have medical uh, students from those hospitals. They just work in my group and then try to work together and see how can get a better system. Okay, technically, brain-computer interface is a microsystem. I mean, if you take look into this architecture of this microsystem, you have different parts. You have neuron probe, and this probe is going to collect neuron signals, and also it's going to go back to stimulate the neurons. Uh, so that's pretty difficult, and this is the part is very essential because it's going to go directly into the brain to do all this work. So in terms of the electric functionalities, you have to be biomedically safe. Okay, it has to be biocompatible, and also have some kind of mechanical properties to be soft enough so it won't damage the brain. And also it has to have some kind of long-term stabilities. Okay, and in addition to the neuron probes, you also have this kind of IC chips. It's going to process this neuron signals. In many cases, this signal, the bandwidth is very large. You have massive data to be processed in real time, so you have very high demand in terms of the capabilities of the chip. It's not only of the computing capabilities, also it has to be very low power consumption because it's going to generate heat when it's calculated. Remember, those chip is going to be implanted together with the probe into the brain. So if you could generate too much heat, it's going to damage the brain. So you have to make a very good balance between the calculating power and the power consumption here. And also, in addition to the hardware, you have to have this kind of algorithm, okay, to try to decode and also to code the neural signals. And in addition to that, you have to make sure all this party, the neural probe, the chip, the wireless uh, antenna, and the battery, everything has to be packaged into a very small microsystem so that you can implant that into the brain. And also, sometimes you need to build up the implantation robot. Okay, it can to work together with the probes, try to do the insertion surgery. Okay, all this is very complicated. So this is a key challenge, as I mentioned a little bit earlier at this talk, which is, you know, in one way, you want to take the full advantage of this technology, which is that you want to get into deeper into the brain. You want to insert as many probes as possible into the brain. But in other way, you want to induce less or minimum damage to the brain. So in our group, we not want to show our advantage in only one point or on one only on one aspect. For example, we can build like 10,000 of probes, which means nothing because you have to have the appropriate chip, appropriate packaging, appropriate algorithm to do that. What we do is we do some trade-off. We just use enough probe and just enough IC chips to do the application. Okay, so this is very typical architecture of how you can use this brain-computer interface technology. Try to do this with the motion recognition. Okay, for example, if you have a patient who's going to suffer from this kind of disease, so what you're going to do is you're going to insert one probe into this sensory area of the brain. Okay, you're going to connect some kind of electrical activities from the neurons, and then you're going to do this neuron signal processing, which we call it neuron decoding, so that you can, interpret intention of this patient. Okay, you're going to do this intention, okay, and turn it into motion control. For example, you have a robotic arm to catch a cup. So that's only part of this loop, which is only part of loop. So in terms of the feedback or in terms of get a closed loop application of brain computer interface, then you have to have some kind of sensors on this arm so you can get for example, the texture, the temperature, the shape of this cup. And we have this kind of coding process, turn this uh, sensing signal into this stimulating signal and using this neuron probe to insert back into appropriate uh, area of the brain so that the patient can sense the feedback of his motion. So that's the typical architecture of how you can use this brain-computer interface technology for the patient. Okay, so what we can do here, we have been talking about brain-computer interface for uh, uh, quite a bit. So we're actually dealing with this technology is indeed the interface between the different parts of within this brain computer interface. We have to make sure our probe is compatible with the chip. The chip is compatible with algorithm, and the algorithm is compatible with the wireless communication bandwidth, and also all this we can have to consider the power consumption and within the physical footprint of this computer, these microsystems. Okay, so now the technology has some kind of trend in terms of how we do this neural interface or with a neuron probe. For example, from very early on, you can only connect single neuron. Now we can connect hundreds of neurons together. Okay, now people are trying to connect 10,000 of neurons together within different part of the brain, so that you can get as many information as possible, so that you can do the accurate coding of the intention of the patient. Also, in terms of the chip, Also, we use more advanced fabrication techniques, and also which can offer us less power consumption and higher intensity density of the chip, so you can process more neural signals. Okay, and in terms of the decoding algorithm, there's a lot of things people have done, so I'm not going to go through this. What I want to try to show you is the progress of our group. Okay, so as I mentioned before, there's many challenges in terms of to developing brain-computer interface technology. There's many some of the challenge come from the technique itself, and some from other parts. So indeed, you're gonna need to get better signal. Okay, in terms of better signal, you're gonna have more abilities to collect more neuron activities. You want to have this long-term recording, and you want to have many neurons into the different parts of brain, so you can interpret or understand the brain better. Also, we need to know better of the mechanism of our brain. Okay, and then there's some kind of like law enforcement we have to think of in a very early stage of developing this technology, because just because this technology may be so powerful and has many potential high level applications, so we have to think about how we can appropriately use this technology for the right purpose. Okay, so, as I mentioned, we have a small startup company working on building up these tools. Because my background is engineering, so what we're trying to do is to build better tools for the neuroscientists, and we're going to build better medical instrumentations for the doctors, so they can use for the patients. Okay, so in terms of the tools, we have different neuron probes, or you can call it electrodes. We have different kinds of IC chips, which can work on collecting the signal, or we can do both collecting or recording and stimulating together. We also develop different kinds of insertion robots, which we can work on the small animals or on non-primate animals, or even on human beings. Okay, so also we have some kind of software which can process the signals, and we have uh, this animal models from different kind of animals for different research purpose and clinical purpose. Okay, so I'm going to show you some results here. So this is we call ECOG electrodes. Okay, so this can apply on the cortex of the brain, so we can map the brain function brain activities during the surgery. And also we have this, implanted flexible neuron probes, which can be inserted into the brain, so it can get the spike activities of the neuron in terms of the spatial resolution of single neuron. And we can do this in hundreds or even thousands of neurons simultaneously. And we have this very deep insertion flexible electrodes can go very deep into the brain and try to collect some deep information of the brain. Okay, so different kind of neuron probes. And we have achieved long-term stability in terms of the probes, which can allow us to record that brain activities nearly 1 year. Also, that's the data of nearly 1 year. Now we have data over a few years. Okay, so also you can do this in terms of neuron recording, which also can do this neuron stimulating. So in terms of this, like mice experiments, we can insert these flexible neurons into the different brain area of the small mouse, and then we just only apply a very low threshold electric current, and we can accurately control its motion in terms of turning it from moving, and we can stop the movement, and we can activate its movement, and we can make it turn left, turn right, and we can do multiple animals together in an array form to do this. Okay, and also this is one thing I want to spend a few moments to elaborate a little bit, because we are working on this flexible electrodes in this area, compared to Neuralink, which is developed by Elon Musk. We have different strategies in terms of how we can apply these flexible probes into the brain, because these flexible electrodes are uh, beneficial in terms of less damage to the brain after implantation compared to the rigid probes. Because our brain is very soft. So if you implanted this rigid probe into the brain, it's going to cause physical damage to the brain. But if we were to replace the rigid probes by those flexible ones, and those flexible ones, because they have very low mechanical stiffness, so it's going to be in terms more stable and cause much less damage to the brain during the normal activity of the patient. However, there comes to a key challenge in terms of using these flexible probes, which is how you're going to implant this flexible ones into the brain, because by itself, its strength is not going to be enough to support itself to be inserted into the brain. So you have to apply external force to do that. So in Neuralink case, okay, they applied a shuttle device. In this case, they attach the flexible probe onto the shuttle device and insert into the brain, and then retract the shuttle device, and the flexible probe is gonna uh, remain or gonna stay into the brain. Okay, that's how they're gonna do that. But here comes some kind of the backside from some kind of like uh, disadvantage of using this kind of strategy, because first you have to use a very rigid shuttle device, and during this implantation, this shuttle device is going to cause damage, physical damage into the brain. And so after you retract those shuttle devices, it's going to leave some small holes due to this implantation. Okay, this one disadvantage number one. And number two is because this shuttle device is so strong and so hard. So if it were to encounter the blood vessels, it's gonna damage the blood vessels, it's gonna cause the brain bleeding. That's a very big problem in terms of the brain surgery. Okay, so in Neuralink's case, they have to open up the skull and try to take a map of where those blood vessels are, especially those major blood vessels are, and they're gonna do this implantation um, to try to avoid this blood vessels. So in this case, they're gonna open up the skull and to find those blood vessels and try to avoid those blood vessels during the implantation process. This is gonna cause in terms of more damage, okay, to the patient, because you have to open up a big hole so that you can see those blood vessels, and after that you're gonna cover up the skull. Okay, so in our case, we try to avoid this problem. We try to insert these flexible probes into the appropriate area of the brain, but without having to open up the skull to try to find where the blood vessels are. So in this case, we play a kind of small trick, because those neural probes are very soft. Okay, very soft. They won't cause any problem to the blood vessel. However, it's just not going to be strong enough to be inserted into the brain. So we applied a coating. Okay, we applied a coating made of silk proteins. Okay, we applied the silk protein to cover up the neuron probe. So to adjust its strength of this coated probe, make its strength between the very soft brain and some kind of harder blood vessel. Okay, because the stiffness or the Young's modulus between the brain and the blood vessel is a few magnitude off. Okay, so we can play this trick to adjust the strength of this silk protein coated flexible probe between the very soft brain and the very hard blood vessel. So in that case, we can insert this protein-coated flexible probe into the brain. So if it encountered a blood vessel, it's going to pass through the blood vessel because it's softer than the blood vessel. It's gonna pass by or pass by the blood vessel without, poke through it。可能这个我用中文说更准确一点，就是你把它插进去以后的话，如果它碰到血管的话，它不会造成这个血管破裂，因为它比血管的强度要低。So if it's not gonna encounter a blood vessel, it's gonna go directly into the brain, right? Because it's stronger than a softer brain. And after implantation, the silk protein coating is gonna dissolve and it's gonna resolved by the brain, and the byproduct of uh, the degradation of protein is just amino acid and peptides, which is totally safe. Okay, so that's the trick. So in that case, you don't have to open a big hole of the skull to see where the blood vessels are. Okay, you only need to, drill a very tiny hole, which is only large enough to get those flexible probe through. And in this case, our device, this probe is only, you know, 50 micron to 100 micron in terms of the waste. Okay, so if we can open up a sub-millimeter hole so that the probe can get passed through, which is going to be quite enough for our implantation. So in this case, our sur surgery is much less invasive in terms of the brain damage here. Okay. So let me show you some results. Okay, we have done some experimental work in terms of the big animal. In this case, this which is on a dog, and we implant this probe onto the motionary part of the brain, so that we can collect or we can record brain activities, and we do the decoding, and we can uh, get very good results in terms of the motion interpretation. And also we can do this on a larger animal, which is a monkey. Okay, so we can train this monkey to play with this very simple game, which is ping pong. Okay, and obviously can play with some kind of this game. In my childhood, we call it 俄罗斯方块. I'm not sure if you have played with this game before. This is quite challenging in terms for a monkey. Okay, and we can nicely train this monkey using our brain connectivity interface to do this. Okay? And after that, we do it on a patient. So in this case, because our human being has much more advanced brain function than a monkey, so we can do it very fast. Okay, it took us nearly 6 months to get the monkey to learn how to play with the game. And in terms of this patient, it only take 8 minutes to do the training, and it can do the same thing. And also, we can do, one-dimensional motion control, two-dimensional motion control, and something like that. Okay. Then after that, we do something more advanced to show the capabilities of our technology and show the potential applications here. We do this language. Okay. So we apply this electrodes on the language area in terms of the part of the brain which is in charge of the language here, and we try to decode the activities of the patient by looking at the brain activities of it. This is our electrodes, and it's applied on the cortex of the brain to cover the brain area of which is in charge of the language here. Okay. And that's how we can apply this technical knowledge for Mandarin decoding. Okay, and then I think let me show you one thing about in terms of the damage of this flexible electrodes or flexible neural probes. This is our probe. If you can see my pointer here, okay, it's very tiny, and we can insert into the diameter or the width of this probe is only 50 microns, and it is able to record the spike information of a single neural activities, and we can do this in a long-term way to do that. Okay, in multiple channels. And last, example I kind of want to show you something we have done recently. So we implant this into a patient, okay, and we build up a software or operating system which can use all these kind of apps, okay. How about Bilibili, email, WeChat, and so on. So it can control those apps and do this operation. They can see a video, you can send an email, it can chat through WeChat, and it can buy something from Taobao and so on. And it can control all this furniture and then the electronics, for example, to turn on a TV and control the AC, air conditioning, and can control the light condition, something like that. And basically, that's all the fundamental need or basic need for a patient which cannot move its arm, or it can do it, and it can control轮椅这一块chair wheel, a chair here, okay, a wheelchair here, to basically to restore its daily operation here. Okay, so that we're pretty excited about this result. Now we're doing more clinical trials to further extend the capabilities of technology, and also we try to optimize our algorithms, try to make this more powerful, and also. Uh, the last thing I want to share with you is I have been spending 40 minutes to try to expand this technology, what we can do. And uh, let's take a step further and think what we can do beyond BCI, right? So we try to build an ecosystem based on BCI technology. What else we can do? Of course, in terms of BCI itself, we can combine both invasive and non-invasive technology together, and we can do, for example, you can basically record the brain activities and try to turn it into intention of the brain, which called it now. And also we can stimulate the neurons and to control the brain activities, and we call it now. And also now you have some kind of like organs on a chip or lab on a chip, so you can culture some kind of neurons on a petri dish and try to connect that and to communicate with a real human brain. That's something we're trying to do now. And also you have different part of this. And, I have been talking about the electric activities of the brain. Also, you have some biochemical activity of the brain, also offer different information of the brain. So we have been working on that. And and people have tried to use BCI with our clinical traditional clinical ways. 中医, for example, they try to use 针灸, and the BCI try to for some kind of special case. Okay, and we have some 有这个我们说类脑和脑机融合这一块，可以说。One thing and one last thing I want to mention, I want to try to introduce here is how we can use uh, uh, AGI and PCI for some unique applications. Now this is how we imagine the future world. Okay, the left part is how you can interpret of the intention of our brain. And the right part is we call it AGI, we call it, 元宇宙, metaverse, and we call it VR, something like that. Okay. Now, what we need to do is how we can translate the intention or the language of a brain into something our metaverse or the VR or AGI can understand. So that's the interface between these two technologies. And that's what we are working on now. Okay, we try to collect as many data as possible from our brain and try to decode the intention or the information or the brain activity of the brain, and we'll try to connect or communicate with this to the right part of the metaverse and try to to build a future world. Okay, so I'm going to stop here, and I'm happy to take any questions. Thank you very much.
Thank you, Prof. Tao. Yeah, for the enlightening presentation. And we will now proceed to the Q&A session. The student may use the raise hand button in the Webex meeting before you asking a question.
Maybe I ask the first question first because thanks, Prof. Tao, for giving us a very fancy Tao is something from fancy science to the actual because it is much more improvement from the last talk by you. And my question is about how about the safety and long-term viability? So what are the most critical considerations for ensuring the safety and long-term viability of invasive BCI?
Yeah, that's indeed a very good question because my group is basically working on the invasive PCI. I know many groups they have demonstrated that capabilities using non-invasive ones, but this basically was very fundamental physics here, right? Because you go in further into the brain, you're gonna have better signal quality, and they have better accuracy in terms of stimulating the brain. But if you think about insert anything into our body, not to mention into our brain, the most vulnerable ones, you have to consider the safety issue in terms of the biosafety of the device itself and the long-term stability of the device. So it comes from a few aspects if you want to consider this challenge. Number one is the materials. Okay, so you have to choose carefully in terms of what kind of materials you are using to build up this device in terms of electrode itself, the substrate, the packaging material, and the insertion material, something like that. So that's why we chose silk proteins as a coating material in terms of other like PLA, PLG, which is also degradable, but it's not that biocompatible if you want to say insert something into the brain. That's materials, and also you have to consider the structure of the device in terms of the width, the length, and thickness, and so on. Because our brain is very sensitive. Okay, it has the most intense in terms of the blood vessel and the cells. It's very sensitive to the implanted device. So you don't want to insert a huge device into a brain. You might be able to insert a big device into other part of body, but in terms of brain, it has to be small, thin enough to do that. It's in terms of structure itself. And one last thing, maybe the most important thing is the mechanical properties, because our brain is very soft. It's very soft. So you have to adjust its mechanical properties to be soft enough so it won't cause damage to the brain once we do the normal movement. For example, as I'm speaking here, my brain is actually moving within my skull, right? If you insert a very rigid probe into the brain, and the probe is gonna keep cutting our soft brain because our brain is moving. So if you have a soft enough flexible probe, its mechanical stiffness or its bending stiffness is so low, so it's gonna move together with the brain without physically cutting the brain. So that's the key why we're going to use the very soft probe for the long-term recording or the long-term operation of this technology. That's why also, I mean, Neuralink, we insist we're going to choose the invasive PCI technique, and also we're going to use flexible probes for that purpose.
Okay, that would be a really nice question answer about that because I also wonder about long-term performance of the device. That will be something because I'm also working on this kind of research. I'm trying to
Yeah,
learn also.
maybe I can add a couple more sentences to that. As uh, neuron probe is not only a implanted device, also has to carry out some kind of electrical functionality. So sometimes we talk about the long-term stability. It's not only about the mechanical stress. It's not only about it might be physically, or damage in the brain. It's gonna probably lose its electrical function due to the long term, because for this implantable device, it's gonna inevitably cause immune response to the brain. So from this immune response, you're gonna have some kind of like scar on the on the probe. It's gonna cover up the probe so that it's gonna get less and less electric conductivity. Okay, so it's not gonna be able to record the electric signal, or it's not gonna be able to stimulate the neurons. It means it's gonna lose the electrical functionalities of that. So that's why we also want to use this flexible approach to cause less immune response, so that it can not only to maintain mechanical strength, also you can, maintain electrical conductivity, so that it can record and stimulate the neurons properly in terms of long term.
Prof, I believe that a lot of students want to ask questions. They are in the chat box. But then your time, I think, is very, very limited. Thanks. But then maybe is it possible for you to choose one or two questions? Maybe you can provide some of a solution to that question. That in the chat box below there on the
Yeah,
right
yeah,
bottom.
I saw a few. So let me just let me
Yeah, maybe choose one or two interesting one.
yeah, I saw something about the long-term impacts. I already answered that, and then the main goal of interface for continuing to change our lives. Okay, so that's something I want to this. The question is, what is the main goal of the interface, and how can brain-computer interface change our lives? I mentioned a little bit during my talk, but the reason why I kind of decided to put most of my career into this technology is I also working on some other projects, but it's something I really want to devote a lot of my time in terms of my resources into this is because I'm not sure if I can somehow use Mandarin to explain that so that I can explain myself more properly。就是说，其实我一直在强调一个事情是什么呢？就是我们人类之所以现在是所谓站在食物链的顶端，或者是地球的主宰，是因为我们的大脑，而不是因为我们其他的器官。我刚刚在我的这个报告里也跟大家说过了，就是我们的五官四肢，其实在某种程度上并不是最强大的，有的是动物，它的视力、它的力量、它的速度、它的耐力比我们要好，但是我们的大脑确实是最强的，所以脑机接口或者 brain-computer interface has the most, you know, potential application, or the main goal is try to bypass our body and try to take the full advantage of our brain to do that. For many sensors, because my major is actually doing different sensors. For example, infrared sensors, for example, those, inertial sensors. Those sensors, we already build many more sensors, which is more sensitive to ourselves. So if we can bypass our eyes, our ears, bypass our eyesight and our hearing to use these sensors to connect those information. Okay, and use brain computer to directly input this information to our brain, because our brain is so powerful, it can process much more data than we have been able to do today. We do not fully use our brain to do that. Okay, that's because we have very limited bandwidth, just limited by our 五官或者四肢。所以如果这些信息的话，我们不用通过我们受限的这些五官来获得，而是通过脑机接口把它输入到我们大脑，我们大脑是有更好的一个计算跟分析能力去做这件事情。This is the main goal of the interface, is try to do that, and also implement another goal, which is 这我可能用中文说的更好，就是我们怎么样去可以实现所谓的永生，对吧？因为我们说这个东西的话，我们人之所以我们大脑其实它的功耗很低的，大脑的功耗大概平均只有20几瓦。就跟一个灯泡差不多。就为什么你早饭起来吃一个馒头，你一天都可以工作？现在用的传统意义上的计算机或者超算，旁边是要有一个发电站来支持它。但是我们身上得病的话，我们其实有很多的机能的失效，很多的这个新陈代谢的需要的话，是由我们整个的身体决定。所以你如果想象到，如果我们有一种技术，我们可以去降低我们其他身体的消耗，就是现在有大家在说的所谓的这个人体的这个冬眠也好，或者怎样也好，但是我们保持我们大脑还是 fully functional。这时候的话，我们通过脑机接口，通过我们大脑，我们依然可以学习、可以交流、可以正常的甚至进化我指大脑。但我们身体的话，就根本不需要这样。那么想想看，一方面我们在地球上，我们有效的生存时间会增强。但如果你想的更远一点，我们去外星球的话，为什么马斯克他为什么想做脑接口？如果你看他的布局的话，他布局 SpaceX 为了星际旅行，Starlink 为了星间通讯，特斯拉为了无人驾驶，Solar City 为了太阳能，Boring Company 为了在挖隧道，无非不就是想要去火星且住下来。 但如果火星不合适，如果有其他地方更合适的话，它在飞的话，可能要几十年、几百年。我们人的寿命是撑不到那个时候的。但如果我们somehow有个技术，可以把我们整个人体的这个新陈代谢可以降到现在的1/10、1%，但是我大脑不要让它休眠，我大脑因为功耗本来就很低，但我通过脑接口的事情，在这漫长的星际旅行间，我依然可以学习、可以进化、可以发展的话，这其实是我想象中未来一个非常大的一个可能性啊！这是为什么我相信马斯克他的脑袋里一定会有这样的意识，为什么要做这个事情？为什么他要需要做特斯拉的这个 Optimus 这个人形机器人，也是这个道理，希望是把我们并不强大的五官和四肢，把它尽可能不用，甚至是降低它对我们这个本身寿命的危害，把我们更强大的大脑通过脑机接口一样这样技术用起来。好吧，很抱歉，这个我刚刚用的是中文，我觉得用中文可能更能表达清楚我对这个技术的理解，跟我对这个技术的憧憬。
Yeah, I believe that because because when the time we are working research, we will use our language just to as a tool to transfer our knowledge and also our ideas. I believe that language is not a barrier, but somehow it's a tool to let people understand what we are doing. Of course, sometimes we don't let everyone know it's okay. Yeah, because when the time we are scientists, we work our own way. I understand that. I still recall what Prof Tao talk about a brain future last year. It is so inspiring when the time we're talking about we don't need our body because our body, our flesh, we have a limitation. So we have a boundary, for example, metabolism and also energy consumptions, and even limit our life. By the time we are, if we can have an interface to translate the data from our brain, maybe we can extend further, right? Because technology we
Yeah.
need time, we need time to have a starship travel something like that, but then when the time we can transfer everything into data, why not we can have maybe long life things, right? But then it will extend to the humans, right? And then it is not like 1 day, 2 days, 1 month, 2 months. It need years. So definitely it's good to have a scientist like Prof Tao to really focusing in this research, because I also focusing. I mean I also keep updating with Prof Tao your daily your working style. That will be something I very much admire too. And I believe that Prof Tao is already provide a lot of insightful things to our student. Of course, we have a student from China too here. I believe that we have a student from Zhejiang University here, and also from Shandong Medical Surgeon. I believe that he also here because he heard about the talk that he want to join too. And I also will copy down the questions from the chat box there, and then to see if I can help the Prof Tao to answer, or maybe Prof Tao have a
Sure.
free time to answer. That would be very nice. Even some of our students they request, is it possible to have your slide? But I believe that it is so much confidential, or maybe it depends on the situation. So I believe this is really nice talk. And Prof, do you have anything you want to advise, maybe in short sentence to new batch of biomedical engineering student in terms of your view, maybe?
Yeah, my background is indeed interdisciplinary because I have kind of emphasized this word many times during my talk, interdisciplinary, because in our world, now the trend of doing research, I think one major trend is to this interdisciplinary work. So in the biomedical engineers, indeed, interdisciplinary area. So you're going to try to learn, not try to master all the area, but you have to learn to try to be able to communicate with people from different backgrounds and try to speak their language and listen to their language and try to think from their point of view so that you can cooperate together. I also advise, be as open as possible in terms of how this technology can go in the future, and be as open as possible, see what you can do and how you can offer to your collaborators, and try to work together and not try to kind of, you know, be a master of everything. You just need to build up your strengths and try to collaborate with others. That's what we are trying to do now. Of course, my background, my strength is in developing those neural probes. And now we're working with doctors, we're working with material scientists, and we're working on computer science, and also we're working with many neuroscientists, try to, listen to their needs okay, and offer what we can do and try to do work together in terms of publish paper together, and what we try to apply our technology to clinical trial together. And I think that's the need. That's the key thing to do this cutting edge stuff. I mean, we don't know. None of us know what exactly this technology can do for us, and when it can be uh, in terms of successful. But we have to believe if we work together, we will be we cannot be open enough. Then we have this can speed up this a little bit. Okay, so that's my advice.
Yeah, that would be nice because multidisciplinary is one of the fancy things in biomedical engineering. We need to have a material science, as what you mentioned just now, mechanical things. Of course, we cannot measure everything, but then we can learn from different people, different needs. So I think this is something what you mentioned. This is something very fancy, and I
Yeah,
believe that we use so much of your time. That this hour is very very much inspiring to us, and then it's our pleasure that I hope every year we can invite you to give us talk. That would be nice because it is something that we don't understand more things. Okay, so thank you
yeah.
so
Thank
much
you,
for the
thank you,
time. Thanks.
thank you.
Okay, thanks so much. I'll keep in touch with you later. Yeah,
Okay,
I will try
thank
to
you.
pay you a visit next month. Yeah,
Sure.
see ya, Prof.
Thank you.
See ya.
I'll see
Okay,
you. See
thank
you
you,
on.
Prof. Thanks.